So I will call this theorem as the existence of inverse Fourier cosine transform. So f absolutely integrable on the semi-infinite interval and this one, the Fourier cosine transform of f. Okay, so this is Fourier transform. And I mentioned that when f is absolutely integrable, then Fourier cosine transform exists. And this one is a function. The semi-infinite interval, okay, of W. So f is a function defined on the semi-infinite interval, and its Fourier sine transform, cosine transform, is also a function defined on the same interval. Okay. Now, if f is piecewise continuous on any subinterval of the semi-infinite interval, and is the right and root cube, and then the left. Oh, I should mention left first. Like I mentioned, and the right and root cube at every point in the semi-infinite interval. Okay. So these conditions for f are common things Fourier series analysis, right? So we usually ask f to have this property. Then f of x can be returned back by taking a similar transform. Okay, very similar to Fourier cosine transform. For all x in the semi-infinite interval except okay, at points say x is 0, where f is discontinuous. Okay, so actually the integral will return back the function value of x at all the points where f is continuous. But when f is discontinuous at certain point x0, then there the value, okay, of the integral. Okay, so the value of the integral equal to the average of its left hand and right hand limit. if x0, if this discontinuity it's greater than 0, or f0, because we have semi-infinite interval, so at point 0 we have only right-hand limit. Okay, so I'll go to the right-hand limit if x0 is the end point 0. Okay, so it is a little bit special for Fourier cosine transform. Okay, so of course, if f is continuous at 0, then it will go back to f0, of course. But in general, it go to the right-hand limit of the f function at the endpoint x equals 0. Okay. So now, this one will be called the inverse Fourier cosine transform. So will be denoted by the inverse of C. Okay? So I have used. Okay? So this is the inverse. So denote as the inverse of Fourier. The inverse of Fourier cosine transform of FAC. Okay? So this is called the inverse Fourier cosine transform of FAC. Right. Okay. So basically you can regard this is a function. Right? This is a function. And this function is equal to the original function f at all x such that f is continuous at that point. Okay, so you can look at, so this notation actually is a function. Okay, it's a function. All right. But a remark. The integral may need to be interpreted as an improper Riemann integral. Okay. When finding so that so this infinity, and here can be regarded as an improper Riemann integral. So this is G. Okay, so we discussed the Fourier cosine transform. Now we will redo the same thing in the other direction. Alright, so on the other hand, we may, because we get the Fourier cosine transform by regarding this function, because this function is defined on the semi-infinite interval. And we can think about f is just the right-hand branch of an even function defined on the whole real line. Okay, but we can do so by regard the same function, right, as the right-hand branch, okay, of an odd function. Okay, so we define the odd function Because for an odd function, the value at x equals 0 should be 0. Alright? So absolutely, we 0. Okay, so we define an odd function. Okay, and this function is defined on the whole real line. Okay, so this is defined for, and it is odd. Now, because we consider f of x to be absolutely continuous, absolutely integrable over the semi-infinite interval. So if we extend to an odd function, this odd function is still absolutely integrable. Okay, it's still. So that, okay, so that we have we can apply the Fourier integral theorem. This is equal to okay for all x in the real line by the Fourier integral theorem. We know the B W is defined by this formula. Okay, by this formula. Right, so we deal with this odd function. So that, but in this semi-infinite interval from 0 to infinity, the odd function is equal to f of x. So this is equal to right, except possibly at the point x equals 0, but for integration, a difference at the point doesn't make any difference. Okay, so we just write down there. Okay, so we have that, and so we see for here. The average of the left-hand and right-hand limit of the odd function is equal to the average of the left-hand and right-hand limits of the original function for all x greater than 0, right? By this definition, for when x greater than 0, they are the same, right? So we get the same right-hand limit and the left-hand limit. So this is true for them. All right. So now, this formula, this equation, can be written equal to if x greater than 0, but this must be 0 if x is 0. Okay? Fine. Because when x is 0, the sign 0 is 0, so the integral is 0. So the value must be 0. Okay? The value must be 0. Okay, so from this discussion, we define, so we have a definition that the Fourier sine transform. Okay, so these two, they, although they have the same sign wx here, but the form is a little bit different because of the vector are different. So for the purpose of symmetry, we purposely define Fourier sine transform of a function f on the semi-infinite interval. So it's defined to be fx defined to be square root of 2 over pi runs to infinity sine. Okay? For all if exists. Okay? So if this integral exists for all w greater than equal to 0, then we have the so-called Fourier sine transform. Okay? This is Fourier sine transform. We use the sine function here instead of the cosine function is there. Okay? So that is the definition. Okay? And with that definition, this one, okay, quite often denoted as Fourier sine transform. Okay, so we use this notation. Okay, so now it is clear that if f is absolutely integrable over the semi-infinite interval, then the Fourier sine transform of f exists. Okay, so we know this exists. Means that we have a function fxk defined on the semi-infinite interval. Okay, when f of x is an absolute interval. Okay. All right, now so again, by the Fourier integral theorem, we have a companion theorem of this one. So it's called the existence of inverse Fourier sine transform. Okay. So again, f is absolutely integrable 0 to infinity, and this one is the Fourier sine transform of f. Okay, and again, which is a function the semi-infinite interval. Okay, so we know that. Okay, so just like the previous theorem, and again we require the same condition. F is piecewise continuous, right? That is on any subinterval of the semi-infinite interval, and as the left hand derivative and the right hand derivative at every point in the infinite semi-infinite interval. Then we can recover f of x by doing the same transform, basically. Okay, so for all x in for x in the open interval, not including the endpoint. The reason is that at the endpoint, the inverse should be come to 0. Okay, it's very special. So so we just saying that except at points x0 where fx is continuous. Okay, and there the value of the integral equal the average of left hand and right hand limit. Okay. Now we deal with the endpoint. If f0 is 0, it happens that the function value of f at 0 is equal to 0, then the value of the integral. Okay, so the value of the integral at x equal to 0 equal f0. Okay, so I think the last sentence is to treat the endpoint in this special situation. Okay, that is the special characteristic of Fourier sine transform. Okay, and so that, and this one will be denoted as inverse sine transform. Okay, the inverse sine transform. Okay, so it is called the inverse Fourier sine transform of f sub x. So that so we get a parallel theorem. Okay, so that is it. Okay, so now basically because Fourier cosine transform and Fourier sine transform are integral transform, right? Because they are integral transform, and the integration is the linear operation, right? It's linear. So so we have a linearity Okay, so we have linearity means that suppose fg they are absolutely integrable functions of the semi-interval. And suppose a, b are real constant. Okay. Then the linear combination of f and g, right, is absolutely integrable. Okay, so it's absolutely integrable semi-interval, and we know that AF plus BG. So the Fourier cosine transform is equal to of the linear combination is the same linear combination back to back to the Fourier cosine transforms of f and g here. And for Fourier sine transform, we have the same result. I think that is to see that why this linear combination is absolutely integrable. Well, we can, if we integrate the absolute value of this linear combination, and we know that this is equal to after bounded by this integral. Okay, after bounded integral. So, and so this is okay. So now we have the upper bound. But we know f and g are absolutely integrable. So this integral is finite. This integral is finite. So this is finite. Okay? So it's very easy to see that the linear combination of f and g is still absolutely integrable. Okay? And the linearity is very easy to check. I think that is the job to you, because that basically is the integral. Okay? It's the integral. Now I state an important theorem will be useful when we solve partial differential equation. Fourier cosine and the sine transform of derivative. Okay, it's about if we have suppose we have an f which is absolutely integrable, and so it has a Fourier cosine transform as well as Fourier sine transform. Now we ask, do we have the Fourier cosine transform and sine transform of its derivative? Okay, so sometimes we need to know. And if it exists, how can we compute it from the Fourier cosine or sine transform of the original function f? Alright, so about f itself. F is continuous. Alright, so f is continuous. The semi-infinite interval, and f absolutely integrable. Alright, on the interval. And f of x goes to 0 as x goes to infinity. Right? So f has three characteristics. One is that f is continuous. So you have f continuous. Second is that f is absolutely integrable. Third is that f of x vanish as x goes to infinity. Okay, so it decay. And how about its derivative? Okay, derivative is piecewise continuous on every finite subinterval of the semi-infinite interval. Okay, so its derivative is piecewise continuous. Then we have the conclusion that if we want, now we can compute, we can find the Fourier cosine transform of the derivative by using the following formula. Is W, okay? So actually I have to say it's a function of W. So it's W times the Fourier sine transform, okay, of f. And we have an adjustment term, is square root 2 over pi times the function value of f is 0. Very special things, alright? Now how about Fourier sine transform? Oh, I'm sorry, I have to write down. Okay, it's as a function of W. I put W here. And for Fourier sine transform of the derivative, it is equal to minus W times the Fourier cosine transform of f. Okay, and no other terms. Okay, just that. Okay, so this is a little bit strange. Okay, and I'm not going to prove this result because I write a much more detailed proof in my supplement. Okay, and the thing is that the important thing I have to highlight is that f should be continuous, because we are going to use the integration by parts. We use that technique quite a few times in doing the Fourier series analysis. But here it's the same. So we use because to apply the integration by parts, you need that the derivative is piecewise continuous. Okay, so that you can decompose that every finite subinterval, all right, into smaller intervals such that f prime is continuous. Okay, f prime is continuous there. All right, and then you can use the equation by parts. So I'm not going to the detail of the proof because time is so limited, so I have to. All right. So let me just address integration. Interpret it we will interpret Fourier cosine and sine transforms as improper Riemann integral and use integration by parts. Okay, so but using integration by parts, we can turn an integral involving f prime to integral involving f. Okay, so that is the reason why we use the integration by parts. Okay, and so for that, we require that f is continuous, and f prime is piecewise continuous. On every finite subintegral of 0 to infinity. Okay, so that is the comment that the idea used in the proof of this important theorem. Okay, so you have to see that the technique is that we interpret the Fourier cosine and the sine transform as improper Riemann integral. Improper Riemann integral means that as we said, for something, we interpret so we evaluate this integral in a finite interval from 0 to L. And then let L goes to infinity. Right? This is so-called improper Riemann integral. Alright? So we prove that. And so we deal with the integral over the finite interval. Right? And then we return an integral involving derivative, right, to integral involving f itself. Okay. So this is the best technique we use. Okay, so so you have to see a difference between these two formulas. Okay, between these two formulas. Now, so to apply the theorem further to the second derivative, of course we can apply them to the second derivative, but we require f and f prime are continuous. Okay, the semi-infinite interval, right? And right, so f and f prime now are continuous, and f double prime is piecewise continuous on every finite subinterval of the semi-infinite interval, yeah. And if f of x goes to 0, f prime of x goes to 0 as x goes to infinity, and f is absolutely integrable. Okay, over the semi-infinite interval. Then, by repeatedly using this theorem, okay, so now the Fourier cosine transform of the second derivative, right? Second derivative here. So we have to say, okay, we have to say that first of all, we know the Fourier cosine transform. Fourier sine transform of derivative. Fourier cosine transform of they exist, and then furthermore, Fourier cosine transform of second derivative, and the Fourier sine transform of the second derivative exist. Okay? So we accept the existence of these two, and then apply the theorem again to say that these two are also existent. Okay, so you can that. Okay, once we know that, and we have. Okay, first of all, because why these two exist? Because that by this theorem, f is continuous as required, right? And the f prime is continuous, so f prime is piecewise continuous, of course. And we know f goes to 0 as x goes to infinity, and f is absolutely integrable, right? It's an integrable here. So we have this and this. Okay? So we have the existence of this Fourier cosine transform of the derivative and the Fourier sine transform of the first derivative. We have that. Now. Okay, so actually, I think I can. I think I have. This is too strong, right? So maybe I have to say. Can be replaced by the distance of FCF and LSF. Okay? This is a little bit stronger. Okay, a little bit stronger. Because if f is absolutely integrable, we know the Fourier cosine transform exists, the Fourier sine transform exists. We know that exactly, right? But actually, to prove this theorem, we just need that these two are existent. We just need that, so we can replace it. Right? And this replacement is important when we apply the theorem to the second derivative case. Okay, so maybe I will. You can read this one again. Can be replaced by the existence of Fourier cosine transform of f and Fourier sine transform. Okay, so that would be enough. Alright, so the existence of Fourier cosine transform and Fourier sine transform of f together with all the other conditions implies the existence of these two. Okay? These two. And then, again, the existence of these two applied with f prime, f double prime, then we have the existence of these two transforms. Okay? So it's very important to know from one step to the other step. So we actually just require this one. Okay, and so now we can write the Fourier cosine transform of f double prime is equal to W f Fourier cosine transform of f prime minus square root of 2 over pi f prime 0. Okay? This one. By applying this formula here. But the Fourier cosine, I'm sorry, but the Fourier sine transform of the first derivative is equal to minus w times the Fourier cosine transform of x. So finally, we have minus w square Fourier cosine transform of f. Okay, and then minus, so square root of 2 pi f from 0. Okay, so we have this one, and the Fourier sine transform of the second derivative, the Fourier sine transform of the second derivative is equal to minus w f cosine Fourier cosine transform of f prime. Okay, but the Fourier cosine transform of f prime is equal to this one, so this will become minus 1 square f Fourier sine transform of f, and minus plus w square root of 2 over pi at 0. Right. So we can obtain Fourier cosine transform and the sine transform of the second derivative directly from the Fourier cosine transform and the Fourier sine transform of f by using this formula. Okay. Any questions? All right. Okay, so let's take a short break now.